Good evening, everyone. Am I audible?
Yeah, ma'am. Audible.
Thank you. So, welcome to the week second of the course. The course name is Water and Wastewater Treatment. So, I'll introduce myself again. This is the second week. My name is Mansi Tripathi. I am PhD research scholar at IIT Madras. So, I'll be taking these sessions and I'll help you solving the assignment problems as well as if there is any doubt, if in case you have, we'll solve that too. So the procedure will be like I'll share my screen. There will be few questions. You can answer them in the chat box. In case of any doubts, you can ask. We'll also try to analyze the questions and means we'll solve them very properly. Okay, so I'll share my screen. Just a second. So welcome to week two of water and wastewater treatment. So now here comes the questions. You can answer in the chat box as well as you can speak in between. So select the correct statement regarding CSTR and PFRS. So this week was mostly about the reactors, and if you will study these reactors properly, you will be able to deal with almost all the parts of the particular course. Reactor is a kind of control volume where we can perform all the reactions. So as you have studied, there will be different kinds of reactors. Like this CSTR is a completely stirred tank reactor. It will be something like this. There will be a tank. We'll put a steering device. Either we'll do steering mechanically or by hand, and the things will go on. Second is plug flow reactor. Here, there won't be any mixing inside. Okay, but all the particles present in a line will be properly mixed. There will be some inflow, there will be some outflow. Here also there will be inflow, outflow. So this is CSTR. This is just for revision. You have studied this thing properly in course. And this is plug flow reactor. Okay. So could you please answer this question? Select the correct statement regarding CSTR and PFRS. I have already given the answer, but you can try to understand. Yeah, you can take your time. Okay, we'll see the answer. You can match the answer whatever you were thinking. So the answer is in PFR the concentration varies along the length. So what happens? What does this mean? This is PFR reactor. If I am putting something of 5 milligrams per liter, at this point maybe it will become 4.5 milligrams per liter. At this point, it is possible that at the next point, it is possible that it may become 3 ppm. ppm and milligrams per liter are same. And while it will leave the reactor, maybe it will become 2 ppm. So what is happening? The concentration along the length of the concentration is varying. So can you give me one example of plug flow reactor? Yes, please give one example of plug flow reactor and one example of CSTR. Very common example which you can see around yourself. I'll give you a hint. It is a water body. In both the cases, it is water body.
Lake and river, ma'am.
Okay, river is what and lake is what?
So river is for PFR and lake is for CSTR.
Very good, very good. In a river, flow is coming from one direction and going towards the other direction. And this concentration is varying around the along the length. Like for example, in Ganga River, it started from Himalayas. It is very pure, no problem is there. Slowly coming to Uttar Pradesh, in Kanpur, there will be some chromium inside Ganga River. While it flows along, slowly, this chromium will reduce. Okay, so this is example of plug flow reactor. Second is CSTR, that is lakes. But the problem here is CSTR. We can lake can be exemplified as CSTR only when the lake is shallow. If the lake is very deep, then only in the above portion mixing will be there, and this mixing can happen by air, or there may be chances of mixing when the temperature will change. Inside water will come out and up water will go down. So this happens when there is change in the season, change in temperature, and this change in temperature happens twice in a year. Okay, when the temperature is changing, then only this will happen. Otherwise it will be mostly air. So that is why this basically happens towards the surface only, it won't go deeper. So CSTR is an example of shallow lakes, and in river this will happen as a plug flow reactor. PFRs are more efficient than CSTRs at same caloric retention time. Yes, this is very correct. When you will solve the example problems, then you will be able to see it better. In PFRs, small volume is required when compared to CSTR. So that is what it means to say. More efficient means smaller volume. We'll see the next question. See, here we have a numerical problem. It will be better if you can solve this and you can give me the answer. We will also solve it, but it will be better if you can solve this so that you can match the answer. You can test your knowledge. Here we have initial dissolved oxygen and we have final dissolved oxygen. And we are talking about the BOD test. 2 ml of wastewater we are adding to 300 ml of BOD bottle. Dilution water has negligible oxygen content. You have noted down the data? Okay, we'll see the next slide. So, BOD is given by BOD initial minus BOD final. So, it's written little complicated. DO initial minus DO final multiplied by dilution factor, or DO initial minus DO final divided by dilution ratio. Okay. So you can see the question again. Initial DO of the mixture and the dilution water was 5.25. Final DO of the mixture was 2 milligrams per liter. BOD test is run by adding 2 ml of wastewater to 300 ml BOD bottle. So the answer it will give is 5. Just a second. Here it's not proper. So it will be 5.25 minus 3, 5.25 minus 3 into 300 by 2. Okay. 5.25 minus 3. I'll check the calculation as well. Yes, this will be the answer. I'll correct this portion and I'll get back to you. Okay. So dilution factor is this and dilution ratio is just opposite, 2 by 300. So DO can be expressed both the ways. Okay, we'll see the, and this is what it is written: of mix, BOD of mix is equal to BOD of dilution water plus sample. Okay, here you don't have to bother about this. The main BOD is given by this thing, initial minus final into dilution factor. We'll move towards next question. This is also a numerical question, but this is, I hope, a little easier. Here we have to take care of the temperature. As you know, as the temperature changes, oxygen content of the water body changes. I hope you know in what direction it will change. Okay, so please try to solve this question, then we will see the solution. You can take 2 minutes to solve this question. It's very simple. You can use your calculator. Try to solve this question. Then we'll match the answers. Okay. Can you try once again?
Ma'am, it is more than 250 milligram per liter.
Yes, 100% correct. See, what will happen when we are talking about dissolved oxygen? So, as the temperature increases, dissolved oxygen decreases. But when we talk about BOD, okay, so the effect will be opposite. That is why when the temperature is increasing, BOD will also increase. Okay, so this will be the case. When we talk about oxygen, it is inversely proportional to temperature. But when we talk about BOD, because this is difference between two oxygen levels, so when we talk about BOD, it will increase with the temperature. I hope you understood. And this, if we talk about this D option, as bacteria cannot withstand such high temperature, so 30 degrees Celsius is very good temperature for bacteria. Okay. If we go more precisely, it's 29 degrees Celsius. So if you are keeping anything at 29 degrees Celsius, bacteria will be very happy to survive on that. Okay. So we can just disregard this option D. We'll move towards next question. This is also a numerical question. Please try to solve this question. It's very simple. This is your equation. Y is BOD. Why not is it ultimate BOD? Because it is asking rate constant in case of E. That's why E raised to power minus KT. K is raised constant and T is time. As you can see, time is given as 4 days. Temperature is given as 20 degrees Celsius. Okay. And BOD, this is equal to 75% of ultimate BOD. So what it is saying? Y upon Y naught is equal to 0.75. I hope this much hint is enough to solve the questions. It's very straightforward. You guys can take a minute to solve this question. Then we will move forward to see the solution. Okay, we'll see the solution. So the solution is pretty much simple. I have shown you this formula. Okay, same thing is written in this one. BOD 4 is equal to BOD ultimate minus, so means 0.75 is equal to 1 minus e की power minus 4k. 1 minus 0.75 is equal to 0.25 is equal to e raised to power minus 4k. When you will solve the k, please check the calculation if this is correct. So according to this calculation, it's coming. How we will do this? We will take ln both the sides. And when you take ln with e, it will give minus 4k. So k is equal to ln 0.25 divided by 4. Solution is very simple. Just you please check this calculation if this is correct. Okay, we'll move forward to next question. Question number 4 is regarding the recovery zones in the river. Okay, so different if we are putting, if for example, let's take example of a lake or river. Let's talk about river. If we are putting any pollutant at one side, so it will, as we have seen in plug flow reactor, it will go with some change. So there will be changes in the level of that pollutant as well as the oxygen present inside the water body. So there will be various zones that will be formed on the river, in the river. So these are the names of different zone. I hope you have studied it very properly. Sir might have explained it very clearly to you. So the answer for this question I need to get. So when wastewater is disposed into a running stream, four zones are formed. Okay. In which of the following zone will be minimum level of dissolved oxygen be found? This is very simple question.
Ma'am, answer A, zone of degradation.
Answer is zone of active decomposition. At zone of degradation, oxygen will be 40% of the saturation. Zone of zone of clear water and recovery are pretty much same. Okay, they will be in the beginning and at the end. Oxygen will be, we assume the oxygen will be up to the saturation. In zone of degradation, the degradation will start. It is just starting. So the oxygen level will be almost 40% of saturation. But in the zone of active decomposition, oxygen level falls very nicely. Okay, so just imagine this is the level of 40%. This is a degradation zone. This is active decomposition zone. This is recovery. This is clear water. This is also clear water. So what will happen here? Zone of degradation, oxygen level is maintained. Here it will drop. After that, it will start maintaining itself again. Okay, so this is what happens at the zone of active decomposition. There will be a sag. This is what we call sag in the oxygen level. Okay, so here oxygen is below 40%, the minimum oxygen level. We'll move towards next question. This is a numerical, quite big numerical. You please take note of all the data, then we will solve the question. TMDD is the name of a toxic compound here. It can be anything. And please make a note of it that it is a batch reactor, not plug flow reactor. We have the initial concentration, we have the uh, like after treatment concentration, and treatment time is 30 minutes, and the rate is first order. You have to consider steady state and treatment system. Oh, here treatment system is plug flow, it's not. Okay, so these are kind of two questions. This is first, in which you have to take care. It is you have to solve. It is at batch reactor. This is second question. Here it is saying 2 milligram per liter is given final in the batch reactor. But in the second part of the question, it is saying that we want 1.5 milligrams per liter. So what will be the retention time? Here retention time is also given, end product is also given. But here you can see what we want. We want retention time, and product is there. Initial concentration is same. Try to solve this question. This is very interesting question, and this kind of question will be there in the assignments as well as in the exams. I hope you are getting what we want to find here. First of all, you have to understand what we want to find. What is the question here? There is something that we need to find that we will use in the second part of the questions. I'll give you one more minute to note down all the parameters, and for those who have joined just now, I'm giving some time to note down all the parameters. Then we will see in the next slide answer for this question. Okay, we'll see the solution. So first of all, we have to apply the batch system, this mass balance equation. Ct is equal to C naught e raised to power minus Kt. Ct is given 2, means that is what we want finally. C naught, it's given 15 milligrams per liter. Time is given 30. 30 minutes. So we need to find out the K. So K, we got this. Please check the solution. I am also checking, but you guys please check the solution. Okay, then it's coming correct in my case. So then we will put the same equation with the changed this effluent concentration. When we will put the same equation, we will get theta, that is time. Here it is represented by t, here it is represented by theta. So we did this just to change the notion so that you won't get confused. Okay, then we got it's 34.26 minutes. We'll move towards next question. Select the correct statement regarding the biochemical oxygen demand, BOD, that we were discussing. We have solved many BOD questions, so this is a kind of theoretical question, very easy for you to solve. Please try to solve this question. Let's see the answer. So the answer is A, C, and D. First is the BOD rate constant varies with temperature. Yes, it follows went off Arrhenius equations. So K at t degree is equal to K at 20 degree theta raised to power t minus 20. Okay, this theta can be anything depending upon this temperature range. The most commonly we take 1.047. This is the most common that we take. 1.036 also, 1.016 also. There are many equations. There are many values of theta depending upon the range of temperature in which we are working. B is the time of self-purification in a stream does not depend upon the BOD rate constant of this stream. So it's wrong. Maybe you have studied this Streeter-Phelps equation, in which in the equation of T we are finding BOD constant also, Kr minus Kd, if you have studied. C is the second stage BOD is due to nitrification demand. Yes, very correct. How is BOD graph? This will be like this, then there will be a jump, then this. So this is carbonaceous BOD, but this is nitrogenous BOD. Not whole, this is nitrogenous BOD. D is the ultimate BOD value of waste remains the same at all temperature. So this is very correct. Ultimate BOD will be remaining same irrespective of temperature. So any doubt on this question? We'll move towards next question then. If any doubt you are getting in any of the questions, please note down in the chat box. We'll deal with them later or maybe in the next class whenever you're getting any doubt. So this is also a numerical question. This session is full of numericals because from this chapter mostly you will be getting in the exams are the numericals. So that's why we have tried to incorporate as many numericals as possible to make the concept very clear. So the question is, in a certain situation, wastewater discharged into a river which mixes with the river instantaneously and completely. Okay, so for example, we have a river, wastewater is coming, and here it is mixing very properly. We have wastewater DO, we have its discharge rate. Like, let's make two columns. Here we will talk about wastewater, here we will talk about river. So wastewater DO is 2.5, wastewater discharge rate is 1.20 meter cube per second. Now river, how much DO is has? 7.8. It's pretty good DO. And the flow rate that we have is here. The important thing first of all that we should notice is the units. Here in both the case unit is milligram per liter and here it's meter cube per second. So we don't have to change anything. If the unit is the problem, unit is not constant, then we have to make it similar. Temperature is given 20 degrees Celsius. What we have to calculate is the initial amount of DO in the mixture. When these are mixed, what will be the DO? So this is a very simple dilution problem. Please, I have already written down all the parameters. Please try to solve this. Then we will see the answer. Okay, we'll see the answer. Answer is very simple dilution problem. Since there was no issue with the units, we can directly put them. And this is what the answer we are getting, 7.16 milligram per liter. Wastewater into flow of wastewater into dissolved oxygen of wastewater plus flow of river into dissolved oxygen of river, and adding both the flows. So this is what we are getting. So coming to next question, it is a softening problem, a very theoretical problem. Water containing high concentration of what makes it a hard water? So as we know, we have different types of water: hard water, soft water. The problem, so the problem related to hard water is the formation of scales in the boilers. How hard water can be seen? When we boil a hard water, it will give a white precipitate. So that is hardness. So that hardness is due to particular salts. So among these, what are those salts? That will,
Calcium and magnesium, ma'am.
yes, very good. So calcium and magnesium is the answer. So coming towards next question. There are two wastewater samples. This is also very simple question. Here we are talking about dissolved oxygen, some theoretical knowledge. So we have two wastewater samples. Let's say A and B. The temperature of A is 20 degrees Celsius and B 30 degrees Celsius. So which sample has more dissolved oxygen? We have discussed in very initial slides. So it will be very simple to answer. Try. You can answer in the chat box also. Which will have less dissolved oxygen or more dissolved oxygen? Or do they have same amount of DO? Or do we need more data to check? Okay, we'll see the answer. So the answer is sample A. As I have already explained, with temperature, the amount of dissolved oxygen in the water decreases. If the temperature is increasing, dissolved oxygen will decrease. So here the temperature of B is more than A. So there will be more dissolved oxygen in A. Okay. We'll move towards next question. So this is also, so this is some information that you need to understand. So what is biochemical oxygen demand? It is represented by this equation. We have seen this in very first slides. So this is not biochemical oxygen demand. This is actually this curve. LT is ultimate BOD. Okay. LT is ultimate BOD. LT is BOD remaining at any time. And K1 is first order reaction rate. T is time. What is L naught? L naught is equal to, uh, actually, what is L naught? Ultimate BOD means BOD remaining plus BOD consumed or BOD exerted. Okay, so what is BOD? What we measure actually is this thing. We never measure BOD remaining. We try to measure how much BOD is consumed so that we can check how much oxygen is consumed. Okay, for that we check BOD consumed. So what is Y? Y is equal to L naught minus L, and this is the equation of LT that we are putting. So Y is BOD exerted at that time. So this slide we have kept to make you understand the concept of BOD. Just a little revision, because in the further all the questions here as well as in the examination and even in the further weeks will be mostly related to BOD. You have to deal with BOD, you have to deal with Strater Phelps equation and all those things. That's why this is just a slide to make you understand, because We have seen many people getting confused between the BOD consumed and the BOD remaining. So in the question, it will be given, a numerical will be given, and we will ask BOD remaining, and there will be four options. One answer will be of BOD consumed. So this is just to make you understand that when we say BOD, it's always BOD consumed or BOD exerted. And this is remaining. So this graph is between LT and T. So this is decreasing, which is signified this by this minus sign. This is next question. BOD of certain water sample was measured as 50 milligram per liter. So what does this mean? The things that I have showed you in the previous slide is kind of correlating with this question. Try to understand this tricky question. What does this mean? This will clear your concept very well. Try to answer the question. So what is this BOD? Is it the dissolved oxygen concentration? So no, it's not dissolved oxygen concentration. It is the amount of total biological organic matter present in the water. So here there is two problems. First, it's not the measure of amount of organic matter. Second, when we say total, BOD is never total. BOD is organic. Organic, that too only carbonaceous. Mostly when we say BOD, it's mostly carbonaceous. It's not nitrogenous. C is concentration of organic matter that could be biologically oxidized. So here also we are talking about amount of organic matter. So no, it's not about amount of organic matter, that if we are putting some 100 kgs of dead fish inside the body, and then we will say organic matter is 100 kg per liter. So no, that is not true. Actually, what is BOD is, it requires 50 milligram per liter of dissolved oxygen. So it is the measure of organic matter, but in terms of dissolved oxygen. Okay, so BOD is option number D. It requires 50 milligram per liter of dissolved oxygen to biologically oxidize the organic matter present in the water. If there is any doubt in this question, if there is any concept clarification required, so you please let me know. We'll solve. The next question is the amount of oxygen required by nitrifiers for nitrification. What are nitrifiers? They convert ammonia to nitrite, then to nitrate. This process is called nitrification. So what is this process called? Ammonia is converted to nitrite, then to nitrate. So this process is called nitrification. So this is represented by,
NBOD.
yes, very correct, NBOD. So I have shown you this graph. Half is CBOD, half is NBOD. This is NBOD, lower is CBOD. We'll move towards next question. This is also a theoretical numerical question involving theoretical oxygen of benzoic acid. So this is the equation given. We know how much wastewater contains benzoic acid, and we need to find out the theoretical oxygen demand. So theoretical oxygen demand is kind of equal to COD, but in general theoretical oxygen demand is greater than COD, which is greater than BOD. This is general scenario, but when we talk about things in practical, we consider both of them to be same, depending upon the compound that we are dealing with. Okay, so this is the equation. Please try to solve this question. This equation is very important. First of all, check if it is balanced or not. Anyway, this is balanced. But the first thing that you have to do always when you are getting any equations is you have to first balance it. After balancing only, you can approach the problem. Please try to solve this question. Okay, we'll see the solution. So to solve this equation, to solve this question, it will be better if you can write this equation first. Then you can calculate the molecular weight of each compound. Each compound means we are talking about benzoic acid and oxygen. So this is molecular weight of benzoic acid and this is of oxygen. So since here it was written to why balancing is important, because we need these values. Oh. So 2 into 122 gram of benzoic acid needs 50 into 32 gram of oxygen. So how much this 370 ppm of benzoic acid will require? 5 into 32 divided by 2 into 122 into 370. This is what we got. So this is the correct answer. Okay, let's move towards next question. This I have just explained. THOD is greater than COD greater than BOD. So you can answer this question very simply. BOD by COD ratio of wastewater sample will be usually greater than 1, less than 1, equal to 1 or 0. So it will be less than 1, because what is BOD? It's mostly organic matter, easily biodegradable organic matter. And COD means non-biodegradable as well as biodegradable. So that is why COD will be mostly higher than the BOD. So that is why this ratio BOD by COD will be less. Moving towards next question. This is also numerical. Standard, here we have to find BOD 5. Standard BOD test with 1 is to 30 dilution. Dilution is important. Initial DO we know. 5-day DO we know. So we have to find out BOD 5. Okay, it's very simple question. It's lab question actually. Here you don't have to use any K values. Just you have to subtract and multiply by the dilution factor. So please try to solve this question. Very simple question. I'll give you the formula again. DO initial minus DO final multiplied by dilution factor. And this is what? BOD 5. We'll see the solution. So the solution is 216. How we are getting? 9.2 minus 2 into 30. 7.2 into 30. Okay, so this is the solution. 7.2 into 30, 216 milligrams per liter. Okay, very simple question. So that's all for today. If there is any doubt, you can ask or we'll close the session. Any doubt in any of the questions? If not now, you are getting any doubts in between, you can ask, okay, anytime. In the next session also you can ask, or you can ask in the discussion forum that is there in the NPTL. Okay, so are there any doubts for now?
No, ma'am, it's clear. Thank
Oh,
you.
okay. Thank you. So, shall we close the session?
Yes, ma'am.
Okay. Thank you. Thank you, everyone. Vimal, your voice is not clear.
No, ma'am, I just said thank you.
Okay. Thank you, everyone. We'll see you next week.